Section 4.5, tangent, cotangent, secant, and cosecant. We're going to get started. See Mr. Hazelwood maybe
because
behind me.
4 is better than 2.
Yep, four trig functions in one section. That's a great idea. So actually tangent, cotangent, and secant and cosecant aren't so bad, especially once you're already used to the idea of graphing trig functions, which we are because we just did sine and cosine. So on this graph of tangent, where we're starting, what we want to notice is that tangent has this like turning point kind of thing going on at 0, 0. Like if you were graphing this yourself, you had y equals tangent x and you wanted to graph it. It hits 0, 0 here, and then it goes up and to the right and down to the left, kind of like a cubic function, not exactly like it, but similar to it. And then here at pi over 2, and at negative pi over 2, we've got vertical asymptotes. So if first, let's say that somebody asked you to graph one period of this, that's all you would have to graph is that section between negative pi over 2 and positive pi over 2, because after that, the graph starts repeating. So this right here would be considered one period, which means that unlike sine and cosine, our period for tangent is going to be pi, not 2 pi. So keep that in mind. That changes things a little bit. If it asks us to graph 2 periods, okay, well, on either side, we'd just draw another part of our graph. Second period. Okay, and then what we need to know about tangent to really understand how this graph comes about is, remember on the unit circle, tangent is our y over our x values. And so that's one way that we could come up with this graph is by taking on the unit circle all of our points, taking the y over the x, and then graphing that. So like at 30 degrees, you'd take the y over the x value and you'd get 1 over the square root of 3, and you'd graph that. And that's a point over here-ish. So the other thing, though, is that tangent is also equal to sine x over cosine x. And that's something that we'll use a lot in here later on, so get used to that idea that it's sine over cosine, which makes sense since on our unit circle, the x values represent our cosine function and the y values represent our sine function. So these asymptotes here are created because of the fact that anywhere that x on the unit circle is 0 or cosine of x is 0, anywhere that happens, we get a 0 on the bottom, which means that we have undefined places. So we're going to analyze this now, and so the domain, to start off, the domain on this one is tricky because it's hard to think of a way to actually put this in interval notation. That would be really challenging, because what we're trying to say with the domain is that, well, it can be any number except for pi over 2 plus any numbers of pi after that. Like pi over 2, for example, is an asymptote. It can't be pi over 2. It can't be 3 pi over 2. It can't be negative pi over 2. It can't be negative 3 pi over 2. And there's infinitely more places that it can't be some number. But it is most numbers, so we can say all real numbers. So you can write ARN or this fancy looking R with a double bar. That means the real numbers. So we can say all real numbers, but x cannot equal, and you just pick an asymptote, so I'm going to pick pi over 2 plus pi k, or k pi. I guess we did k pi in the other section. Doesn't really matter the order because it's multiplication, but something like that. And what we're saying is that we can plug in any integer for k, and we can end up with an asymptote somewhere on this graph. So if we asked you for like, hey, name where 5 of the asymptotes are, you could plug in 5 numbers for k and it'd tell you where 5 different asymptotes are. So we need to say what k is, and so here's a fancy mathematical way of saying that k has to be an integer. You say k, you put a fancy looking e, which means is a part of, and then the set of integers is a z with a double bar in the middle, which Mr. Hazelwood is a really big fan of writing. He thinks it looks really cool.
Z is so cool, I love it.
Yeah, so that would be the domain. All real numbers except x can't equal pi over 2 or anything after or before pi over 2 that is pi away from pi over 2. That's what we're saying. The range is all real numbers or negative infinity to positive infinity, because if you look at our graph, we go up forever, we go down forever, there's nothing stopping our range. It is not continuous. We could say it's continuous on its domain, or we could say that it has discontinuities at, and then we could say the same thing that we said earlier, x equals pi over 2 plus k pi, where k is an element of z integers. That's why it's a z, because if you say it in a fancy accent, it's z integers. Yes, so let's think of some other stuff, like how about increasing, decreasing, or constant. If you look here, between our asymptotes, that graph is increasing the whole time. So we could say that it's increasing on its domain. It never, ever, 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 in this case with y equals tangent x, decreases. So it's increasing on its domain. Well, if it's increasing on its domain, that means that there's no extrema, because extrema, maxes and mins, happen where we switch from increasing to decreasing or decreasing to increasing. It is symmetric. If you take the first quadrant and you rotate it around, it does match up with the third quadrant, and you can kind of think of it like the cubic function. You know, that one was symmetric about the origin as well, and it looks similar to that. So symmetry about the origin. Which the symmetry about the origin means that this is an odd function. Don't forget. This is not bounded because we can get to positive infinity and negative infinity for our y values, so it's not bounded. The end behavior on here is kind of weird, because think about if we start trying to go really, really far to the right on our graph, well, we keep repeating it. It's kind of like this is oscillating. It's not oscillating in the same way that sine and cosine are, but our end behavior will actually end up being does not exist, because it depends on where you stop. And the whole idea within behavior is that you're never stopping. You're going to as big a number as you can. Well, if the biggest number we can get to is an asymptote, you know, then we could talk about the end behavior. If we knew what that biggest value was, we maybe could say something, but we don't, because we're trying to just make the graph keep going on forever. So both directions, it does not exist. Missing one.
End behavior.
I did end behavior.
Asymptotes.
I did not say asymptotes. There are vertical asymptotes at x equals, same place that we talked about earlier for discontinuities and for our domain. There are no horizontal asymptotes though, just the vertical ones at x equals pi over 2 plus k pi. That's analyzing tangent. Example 2, cotangent. So cotangent's just a little bit different in a few key ways from tangent. If we look at this on what was it? On tangent, we had a point at 0, 0. That's not the case on cotangent. We have a point, the important point, like when we're graphing, is that we are at pi over 2 at 0. And then cotangent goes opposite of tangent. It goes up to the left and it goes down to the right. So that's something to keep in mind. Our asymptotes here happen at different places. We have one I just drew at negative pi. We have one at 0. We have one at pi, 2 pi. So this one, it should be pretty easy to see. Hey, those asymptotes, those are pi apart. Between 0 and pi, there's pi distance. If you were asked to graph a period of this graph, you would put a point at pi over 2, 0, go up and to the left and down and to the right between your asymptotes at 0 and pi. And if it asked you for 2, you could go on either side and draw another period of that. So just like with tangent, cotangent's period will be pi, unless we have some sort of horizontal stretch or shrink. So we can analyze this graph in a very similar way to what we did with tangent. So also, cotangent is our x over our y on the unit circle, and it's cosine over sine. So the reason that this is different from the reason this is so different from tangent, but also, excuse me, very similar, is because we're just basically doing the reciprocal of tangent. That's what cotangent is. It's the reciprocal of tangent.
It's upside down tangent.
Yeah, so instead of our x values being 0 causing problems, it's the y values that cause those asymptotes.
Because it's the reciprocal.
Right. So for our domain, just like with tangent, we're going to do a little fancy, it's all real numbers, except x cannot equal. You pick an asymptote, and then you add plus k pi to talk about all the other asymptotes. And here's what is interesting. If you pick 0, hey, that's where an asymptote is, and then you add k pi.
You end up you get k pi.
You just get k pi. So we're saying that 0 plus k pi, if that doesn't work for you, if it makes you uncomfortable, you could put pi plus k pi instead.
You could be the same thing.
Yeah, and then we say k is an element of the
there it is. There it is.
integers.
Is it integers?
Okay, so
We're French.
yes, we are, but not really.
Okay.
Oui.
Oui.
That's all I know. Okay, range, same as tangent, is negative infinity to positive infinity, and the continuousness is
Continuities.
there are discontinuities at all of those places that we just mentioned.
That mess up the domain.
X equals k pi when k is an element of the integers.
And also, while we're talking about that, we might as well throw out the old asymptotes right there.
Right, the vertical asymptotes are
At the same places.
Place. Good call. Now,
So there's a bunch of stuff that happens, right? There's a bunch of stuff related, and if you're paying attention on tan and cotan, there's a bunch of stuff that's related with where these discontinuities occur.
right. And symmetry, there is no symmetry.
I believe there's no symmetry on this one.
Because you could maybe say, oh, it kind of looks like y-axis symmetry, but if you actually think about flipping it,
Right.
those
It's got to
don't
be a
actually
mirror
match
image.
up.
It's got to be a mirror.
They're not mirror.
Out there, yeah.
No, they're not.
It'd be like me looking in the mirror and seeing Brad Pitt.
Those are
It's not happening.
That's not a real reflection.
That just
That'd
like
be
that is not a real reflection.
Right. Okay.
Okay.
It's not increasing the whole time this time. It's decreasing because we flipped everything. So it's decreasing
Over its domain.
over its domain or on its domain. And what else can we say about this? There are no extrema.
The end behavior is basically non-existent.
Right. And for the same reason as for tangent and for sine and cosine for that matter. Same reasoning that whole way, that we can't just stop at some place and say, oh, well, I'm going to pick the end behavior now.
And look, we're close to 0. Or look, we go towards infinity. It just bounces all over the place depending on where you stop. Like, I could choose one place to stop, and Mrs. Stevenson could choose one place to stop, and wherever you are, you could choose some place to stop, and we could all choose different places and get different answers.
Yeah, and that's not how end behavior works. We should all get the same answer, assuming we all know what we're doing.
Right.
It's not bounded because we can go up top and down to the bottom. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's everything for cotangent.
Secant. Now, the secant graph, if you're looking at this, you're like, oh my God, how am I going to draw that? I'm telling you, it's the easiest. It's one of the easier ones to draw. Here's what you're going to do. This is exactly what you're going to do. You're going to graph, you're going to graph the cosine curve.
So cosine because this equals 1 over cosine.
Right.
So we're going to graph cosine. Cosine starts at 1 and has a period of 2 pi. So remember we talked about how to graph that. We make a mark halfway, halfway, halfway. And so it starts at 1, it comes down here to the middle, ends up at our bottom amplitude, comes up here to the middle, goes to our top amplitude. So just going to draw this.
And you're going to draw it exactly how Steve's doing it right here. And get the whole explanation on this. When you see secant, draw cosine first.
And
that's first order of business.
Preferably do it maybe just a little bit lighter or in a dashed line, but it needs to be there.
Yeah, you need to be able to see it because it'll make the secant graph actually stand out so that you can get it correct.
Because here's what we do to actually finish this off. If we were graphing this, we'd have our cosine curve right now, and then we'd say everywhere that it goes through 0, that's where cosine is 0, so it puts a 0 on the bottom, so that's an asymptote.
Right.
So we draw our asymptote lines every place that it touches 0 with some elevator music. Okay, so we've got asymptotes there. And then every place you have the top of your graph.
That's the bottom of the secant.
Right, so it kind of looks like a parabola.
Right, but it's not.
It's not technically a parabola, but at the top you draw a U shape going up, and then at every bottom you draw an N.
Right.
So U's and N's.
I'll be right back.
So our domain, just like on tangent and cotangent, we've got these pesky little asymptotes. And by the way, our period for secant is the same as our period for cosine, because we have an upward U, we have an N, and then after that it starts repeating itself. So our period here is 2 pi. So for our domain, we need to pick where one of our asymptotes is and then add 2k pi. Just like whenever we started talking about stuff with sine and cosine, and we used 2k pi. So this asymptote right here, I kind of marked over my tick marks, 2 pi, pi, so that's pi over 2. So we're all real numbers, but x cannot equal pi over 2 plus 2k pi, where k is an element of
real. I love those z's.
Yeah.
Those z's are so fun.
Okay.
You should practice just drawing those. They're a little trickier than you think.
The range, they are. The range, now this is interesting because our range for cosine was -1 to 1.
And never above that or below that, ever.
Right, but this is actually going to be like the opposite, because look, we've got values starting at 1 going up, starting at -1 going down, but nothing in between -1 and 1. Because remember, this purple dotted line, that's not really there. It's not really part of our graph. It just helped us graph it. So our range is from -infinity to -1, and it does touch -1.
It does touch 1. Now, this is, in the past when we've analyzed some graphs, Mrs. Stevenson and I have given you a little bit of freedom maybe. Is it included? Is it not? You can make an argument either way. Look, -1 and 1 are included on this one. You have to include it. You need to be very clear that this is a bracket, not a parenthesis.
Right. Our discontinuities...
That's going to be related to your domain, just like your vertical asymptotes will be related to domain, just like they were related to domain on tangent and cotangent.
So we'll just knock all of those out right here. Discontinuities at pi over 2 plus 2k pi, and vertical asymptotes.
Little VA action.
And are there horizontal asymptotes?
You know, a horizontal asymptote is a great question to ask on this, but you know, horizontal asymptote's a description of end behavior.
And when we get to end behavior, which we can do right now if we want.
We keep bouncing around. We don't really get to anything at all because just like the previous problems,
it keeps going up and down.
It just keeps going up and down. And so it just depends on where you choose to stop. So no horizontal asymptote.
No horizontal asymptote. Symmetry, y-axis symmetry, just
Definitely
like cosine
y-axis.
had.
So this is going to be an even function, which means you can put a negative number in and get a positive number out.
Right. We've got difficult increasing, decreasing situation.
Here we go.
And maybe
hang on to your hats, kids.
Maybe first let's talk about the maximums and minimums, because
let's do that.
I've got a minimum right here.
I have to say, I really like your color choices this morning.
I accidentally there's this like crayon box over here that I have no idea how I made it show up. 0, 1 is a minimum. Over here.
Right there.
2 pi.
Right there.
You just touched their face. That's weird. 2 pi, 1. I'm just kidding. Okay. That's another minimum. And then here's a maximum down here at pi, -1.
Right.
So
it's kind of backwards than what you might think.
Right, because the mins are the ones on the top of the graph.
Right.
But they're where we're switching from decreasing to increasing.
Right.
So if we write this, our minimums are happening, well, there's one at 0, and then there's going to be one every 2 pi before and after that. So 0 plus 2k pi is 2k pi, 1, because all our mins happen at 1. Now these are local minimums. That's why our minimums are higher up than our maximums.
Right.
Where k is an integer. Our maximums are everywhere that we have.
So you're going to start at pi,
and then every 2 pi
and then you
before
got to
and
add
after.
2 pi after that, right?
Pi plus 2k pi, comma -1, where k is an element of the integers. So this is increasing. Let's see, from...
So now use your max and min information to determine where this is happening. And by the way, this can be really challenging working all this out. So this could be something where you might not get it right at first, but just keep doing like we're showing you right here. And eventually, if you keep doing it like we're showing you because we said so, eventually it's going to click in.
Yeah. So this interval right here is from 0 to pi over 2. It's increasing here. And it's also increasing from pi over 2 to pi. We have to break that up because of this asymptote
Right.
line.
We can't do anything on an asymptote.
And also, we want to add 2k pi to everything because we want to talk about all of the situations. So we've got 0 plus 2k pi, which is 2k pi, comma, so that's 0. Then pi over 2 is where that one ends, pi over 2 plus 2k pi. And then also it's increasing from pi over 2 plus 2k pi, comma, 3 pi over...
I think that's 3 pi over 2.
No, that's pi.
No, it's pi. It's pi.
It's right there.
Pi.
Plus 2k pi.
And notice with this, everything's in parentheses because we cannot include, include asymptotes.
You can't include pi over 2. We could put a bracket around the first one at 0
right.
and at the last one. But I like to play it safe and just put parentheses all the time personally.
But on a situation like that, also check with your math teacher and just make sure, because some teachers are going to actually want to include that actual point where the minimum or maximum occur.
Yeah, the crazy ones. Pi to 3 pi over 2 is where it's decreasing. I don't know what that was.
That's crazy. Crazy teacher.
Oh, okay. Pi plus 2k pi until we get to 3 pi over 2 plus 2k pi. That's from here to here.
Yeah, from there to there.
And
right.
then from
I couldn't
here
have drawn
to
it any
here,
better.
3 pi over 2 to 2 pi. So to what? 2 pi? 2 pi plus 2k pi.
With KEZ.
K is an element of the integers. So domain range.
I think that's everything.
7, 8. No, we are not
bounded. It is not bounded.
Because we can get to negative infinity and positive infinity for our
There's no floor,
values.
no ceiling.
Yeah, we've got a little weird thing going on in the middle, but what matters is at the top and the bottom it is not bounded.
That is correct.
So cosecant is similar to what we did with secant, but also we need to know that it matches up with not the same function, but the opposite function. So cosecant is 1 over sine. And so what we would do to start graphing this is we would graph sine. So we start at 0. We have to end by 2 pi, so we go halfway, halfway, halfway. So we start at 0. We are up at the top by pi over 2. We're in the middle by pi, bottom by 3 pi over 2, back at the middle at 2 pi. And so we graph this first part here. And then we can go the other direction and continue our graph. Okay, but what you do here is you graph sine, and then just like with secant, we draw asymptotes where our graph is 0. And everywhere there's a top value, we draw a u going up. Everywhere there's a bottom value, we draw a u going down. That's how you would graph cosecant. And then from there, let's analyze this. For one thing, we can look at a period of this as being like from 0 over here to 2 pi. So the period of this is 2 pi, just like it is for sine. Our domain is all real numbers, except x cannot equal, well, there's an asymptote at 0, so it would be, So it would be x cannot equal 0 plus 2k pi, but since it's 0 plus 2k pi, we just need to put 2k pi, where k is an element of the integers. The range is just like it was for secant, that we can go from negative infinity to negative 1, and we can go from 1 to positive infinity. The discontinuities happen at all of these asymptotes. So at x equals 2k pi, where k is an element of the integers, then we can say the vertical asymptotes are at that same thing, x equals 2k pi. K is an element of the integers. It is not symmetric. It is symmetric, okay, just like sine was, because we can take this quadrant up here, this first quadrant, and we can rotate it down here to the third quadrant. That's symmetry about the origin. Which makes it an odd function, just like sine was. It's not bounded. The end behavior does not exist. We can look at our maximums and minimums here. Here's a minimum that is happening at pi over 2, comma 1. Here's a minimum that's happening at 3 pi over 2, comma negative 1. And you just have to pick one of each of those points and then realize, hey, these are, all of our maxes are happening 2 pi apart. All of our minimums are happening 2 pi apart. So the maximum happens at 3 pi over 2 plus 2k pi, comma negative 1. Because remember, our maximum's top is the top of like a hill. Our minimum is the top of a valley, the bottom of a valley, pi over 2 plus 2k pi, comma 1. And then we look at increasing, decreasing. Based on that, it is increasing, we could say, from pi over 2 to pi, and from pi to 3 pi over 2. And also it's increasing from pi to 3 pi over 2. It is decreasing from, we could pick this over here, from negative pi over 2 to 0, and from 0 to pi over 2. And so instead of putting 0 plus 2k pi, I could have just put 2k pi. So I'll do that here, 2k pi to pi over 2 plus 2k pi. And each of these 5 right there need to have k as an element of the integer, since we used k in all of those. And that's everything for cosecant. Alright, we're going to do some examples now of what to do with tangent, cotangent, secant, and cosecant. So, describe the graph of the function in terms of a basic trig function. Locate the vertical asymptotes and graph 2 periods of the function. So, with tangent, the number in front here is not really going to be an amplitude, because we don't have amplitude if you think of the graph of what tangent looked like. It's still going to tell us about a vertical either stretch or shrink. So in this case, we don't have a vertical stretch or shrink. The number inside here does affect our period. This is still b, but our period for tangent and cotangent, since the period of those is pi, then we do pi over b, not 2 pi over b. So in this case, it would be pi over 4. That's our period. And that's going to be important. Also, that means that there is a horizontal shrink of 1/4. Because remember, we do the opposite of whatever is next to x. So we take the reciprocal, it's the horizontal shrink of 1/4. That's the only thing that has changed between our normal tangent graph and what we have. It asks us to locate the vertical asymptotes and graph 2 periods. I feel like it'll be easier to locate them once we've looked at the graph.
I agree.
We said that tangent would start at 0, 0. If it's not shifted left or right or up or down, it normally starts at 0, 0. It goes up to the right, down to the left. And since we shrunk by 1/4, instead of our asymptotes being at pi over 2 and negative pi over 2, we are a 1/4 in. So we need to multiply pi over 2, which our normal asymptote place, by 1/4. That means our asymptotes are going to be at positive
8.
Pi over 8 and negative.
And look how Mrs. Stevenson just drew this. She's labeling her points, but she's starting with one that we're going to use.
Yeah. Because really the rest almost don't even matter. I mean, they matter. Do you need to tell them about their groups?
No, we'll be okay.
Okay. So there is one period, and then we would go a period over. Our period here is pi over 4.
So you're going to add that.
This is pi over 8, so we have to add pi over 8 plus pi over 4, which requires some common denominators. This needs to be an 8, so we put a 2 on top. That's going to be 3 pi over 8 is our next asymptote.
So it's just like adding fractions in like 5th grade or whatever,
Right.
but the pi is what can be a little bit
Right.
confusing.
And then halfway in the middle here, that would be halfway between pi over 8 and 3 pi over 8 is 4 pi over 8, and you divide it by 2. And between pi...
Would you, hold on. Okay, now go.
Halfway between pi over 8 and 3 pi over 8, you would add those together and get 4 pi over 8, which is pi over 2. Divide pi over 2 in half, and you get pi over 4.
Right.
That's that middle point. It goes up and to the right, and
Down
it goes down to the left. That's
just like the
period.
first one was.
So the vertical asymptotes here are at x equals pi over 8.
Plus the period now,
plus,
so pay attention.
Plus pi over 4 times k, because our period is pi over 4. K is still an integer. And then for this one, again, this 2, there's no amplitude for tangent or cotangent, but this still means that it's vertically stretching
by a
2.
factor of 2.
And inside here, this 1/2, we flip that and we say, well, that's a horizontal stretch
by 2
as well.
Because it's a reciprocal on the inside.
And our period is going to be pi over 1/2. So we flip the 1/2 up and multiply, and we get, oh, the period's going to be 2 pi.
Hey, we can work with that. It's a lot easier to work with.
Right. And so cotangent starts at our normal asymptotes are at 0 and pi.
Right.
So we're going to have an asymptote at 0 still, but our first one's going to be over here at 2 pi.
All the way over at 2 pi.
And then for our second period, let's go to the left 2 pi.
Right.
And then what happens is halfway between here is our middle point. It's stretched by 2. That's going to be hard to represent. It goes down faster, it goes up faster, but it's going to be hard to represent graphically.
It will be. But you can maybe draw a 2 on there on the y-axis, and halfway between pi and 0, you could put it through there.
Yeah, we could try to do that. I didn't really have a very big graph to try to do that.
Right.
But there you go. There's 2 periods of cotangent.
All right, solid.
Example 6, we're describing the graph of the function in terms of a basic trig function like sine, cosine, tangent, secant, cosecant in these 2 cases.
They operate the exact same way. So if you recognize how they go as sine or cosine, you should be able to do it as well.
Right, and we're going to locate the vertical asymptotes, graph 2 periods of the function. So this first one is related to secant, just normal secant x. And what we've done to it is we've got a negative in front, which
going to reflect over the x-axis.
Reflect over the x-axis, okay. And then we've also got something going on inside of here. We've got x over 3, and so just like with all of our other functions, that's a 1/3 x, which means it's a horizontal stretch of the reciprocal, which is 3. So to graph this, because that's that first part, to graph this, what do we need?
You know what? We need amplitude, and I would find amplitude period of cosine.
Okay.
Personally, that's what I would personally
remember that this is going to go right along with negative cosine of x over 3. All of these things that are happening to secant, we're going to draw a cosine graph where all the same things are happening.
With dotted line or a lighter shade of pencil or however. Just
yeah, different colors, something that shows that it's not really part of the graph. So our amplitude for the cosine curve is 1, because that's what's in front of cosine. It's a period of 2 pi over 1/3. So that's going to be
6 pi, which
pi.
there's your stretch right there.
Yeah. And so to graph this, I would graph first and then look at the asymptotes personally.
Yeah, totally graph first. Now, the fun thing that we can do about this that's really nice is we can take this graph and we can actually label the axis in a way that will work for us.
Right, because it just specifies 2 periods. So let's do 1 positive period and let's do 1 negative period, and then our graph will be nice and not necessarily symmetrical, but balanced. I don't know. The y-axis in the middle, that's always nice.
Y-axis middle.
So you make a point halfway, which would be 3 pi.
And then super halfsies.
We're going up to 1 and down to 1, by the way.
And remember, with secant and cosecant, you're going to need to go above and beyond the amplitude, because that's technically where this graph is located.
Right.
However, we need to know what the amplitude is.
Yep. Negative cosine starts down here at -1. And then it will go up, and then it'll go up, and then it'll go middle, and then it'll go down, and then we can continue our pattern this way, and then we're going to connect these with dotted curves.
I would use a dotted curve or a very faint pencil curve. Or, you know what, if you wanted to be really fun, you could graph this and then graph your secant curve and then go over that with a highlighter or something. Something that emphasizes that there's a difference. Yeah.
Right. So then what we do is every time the graph crosses the middle here,
the x-axis.
The x-axis in this case is the middle, but in another case it may not be. So where it crosses the middle, that's our asymptotes. Go to the top of your graph and draw U's going up.
Not parabolas, but U's.
And they're going to look
They're
pretty
going to
similar.
They're going to look similar, but there's a difference.
And then on your valleys here, you draw them going down. So, and if you want to look super fancy, then you
add
do
that
like
half and then add the other half.
Right.
That's what the cool people do.
Yeah.
So
that's our graph, 2 periods of the function. Our vertical asymptotes are at x equals, and we're just talking about the ones that we see here, or do we want to list all of them?
We can list all of them pretty easily because it's periodic. So,
yeah,
we know what our
pick
period is.
one.
And so that's going to be 3 pi over 2.
Right, it's halfway between 0 and pi, so that's 3 pi over 2. And then it happens
every 6 pi units after that.
Well, but actually...
Well, half of that,
half
I guess.
of that
every
because,
3 pi units.
Yeah, because there's 2 asymptotes for each thing going on. Because there's one here, but then the next one happens over here, which is 3 pi away.
Yeah, 3
okay.
pi. So plus 3k pi.
3k pi.
Where k is an element of the reals. I love, write the z. Write the z.
You mean, yeah, you said reals, but you meant
integers. Yes, I meant integers. God, I love the z.
Okay.
Okay.
Awesome. That's how you do that one. So let's graph a cosecant one down here.
We're going to graph it in a very similar way.
So we took cosecant, a normal cosecant graph, and we are vertically stretching it by 2.
Now that pi in there, don't be confused. Pi is greater than 1, and so what that means is we're going to actually have a horizontal shrink of pi units. So that's a little bit weird, but it's all good.
Of
it
1
all
over
works out good.
Pi
Yeah,
units.
yeah, 1 over pi units, right. That's what I meant.
Yes. No, yeah, I got it. Shrink. Because you always look at the reciprocal. The reciprocal of pi is 1 over pi. And if you think about it, 1 over 3.14 is definitely less than 1.
Yes, definitely, yes.
And then the plus 1 out here, when we're adding 1, that is a shift up of 1. And then when we graph this, what we're really graphing is 2 sine pi x plus 1 first.
So the graph of this, you're going to go have an amplitude of 2, and you're going to have a period of 2 pi over pi, which, hey, that's real numbers.
Right.
Like for real, like that's an integer.
Okay, because the pi's cancel out. And that seems weird because we haven't had that come up very much.
No.
But this is
Totally
actually,
legal.
And actually, in a real world kind of situation, it's more likely to have this happen if you think about it, because our period could be something like, well, something's going to repeat every 2 hours.
Right.
It's a lot less likely for something to repeat every 2 pi hours.
Right,
What does
right.
that even mean? So let's graph. So we need,
Really digging the colors today.
Yeah.
I'm gonna have to mental note to self to
I did
use
it
this
totally
particular
by accident. I don't even
color
know.
scheme.
What else do we need? Half-C's again.
Half-C's again. And we also need amplitude.
Of 2.
2. Now, there's a couple things going on here, because remember, we're going to actually have some shiftage.
Oh, right. So we don't... Here, let me back up a sec. You're right, absolutely. We are going up to 1.
Let's start up 1, and then go up 3.
Up to 3.
Up to 3,
Got
and down to
1,
negative 1.
up to 3, and then down to negative 1. That was an
we
example the other day, actually, where that kind of situation happened. And so we talked about whenever we graph this, how it might be helpful to put, this is not an asymptote line, this is just a dotted line. This is like our new x-axis as we're graphing.
This is a where we start line.
So sine starts at 0.
And goes up.
Or it starts in the middle in this case.
Right.
Goes up to the top, back to the middle, down to the bottom, which is negative 1, back up to the middle, over this way.
And rinse and repeat,
down,
just like shampoo.
Middle, up, middle, and then just connect it. Here's our
There's
sine
a lot of
curve.
dotted lines going on here, but remember, we're really interested in the one that makes the wave curve, okay?
Right. So you could even, technically, if you wanted to, you could even erase the dotted line,
Right.
the x-axis one. But
now,
don't erase.
on the
that's
previous
silly.
example, I said that we were looking for places where we actually cross the x-axis, and Mrs. Stevenson said where we're in the middle, and both
Right.
of us are true. And this is a case where we're actually in the middle. Is
Right.
where we get the issue.
Right, because we have this shift up of 1. If we didn't have a shift up of 1, this would be going through the x-axis here at negative 2. So that is where my asymptotes are, is everywhere it crosses that middle line.
And if you don't believe us, just check out those numbers inside the graph and see what you get.
And basically, every time these asymptotes should happen somewhere where it's switching from a hill to a valley.
Right.
So you should never end up like marking right here and having a random asymptote.
No,
That's
no
not gonna
random
happen.
asymptotes.
So finishing off our cosecant, we've got up
Here's
here.
the solid lines. Bring on the solids.
And then we can really easily list our asymptotes. X equals, you pick one of them, so
Just
we
one.
can pick 0.
I say 0.
So 0 plus half of our period is 2, so that would be 1k. So that's
Hey, Quinn.
really just k, where k is any integer. If you think about it,
there's the z.
if you think about it, okay, let's think of all of our numbers for k, not all of them literally, but k can be 0. There's an asymptote at 0. K can be 1. There's an asymptote at 1.
Negative 5.
And we don't have that drawn, but there'd be an asymptote there.
Right.
So that's what's going on with that. All right, now this is going to be just a little bit different than what we've been doing. It's asking us to solve some equations. Example 7 here. Solve for x in the given interval. You should be able to find these numbers without a calculator or your unit circle using reference triangles in the proper quadrants. So what we're going to do here is we're trying to find x where cotangent of x equals negative square root of 3. Now keep in mind that means we're trying to find an angle, because normally we take cotangent or whatever of an angle. So I'm going to draw a picture, and I'm also going to think about how cotangent is our x value over our y value, or you could think of it as your adjacent over your opposite. And let's make this a fraction, negative square root of 3 over 1. But actually, it could end up being that the negative's on top, or it could end up that the negative is on bottom, and that's something we're going to have to figure out. It tells us to do this in the interval it gives. It gives us pi over 2 to pi. Pi over 2 is right here, straight up. Pi is right here, going to the left. And so our graph needs to be in the second quadrant. So whenever back a little while ago in 4.3, we talked about how if they give us only one piece of information, like cotangent of x equals negative square root of 3, how that gives us 2 triangles, which is what's going on here. But because they gave us more information and gave us an interval, now we're only going to have one place. So we can draw our triangle here. We're going to have to go negative for our x value, so that's going to be this situation, negative square root of 3 and up 1. And so what we want to do is we want to figure out what is this angle to get around here. Well, hopefully we can look at this and say, well, I know what this reference angle is because this is a 30, 60, 90 triangle, and so this is 30 degrees. And so that means, since 180 is over here, that means that to get around to this line, I'm 30 degrees short of 180, so we would subtract and get 150. And that's one possible answer, but keep in mind it gave us this interval in radians, which means that we need to have our answer in radians. So if you get the answer in degrees, you can convert by timesing by pi over 180, or we could have earlier, we could have said, oh, this is, instead of 30 degrees, we can think of this like pi over 6, okay, and then we're pi over 6 short of pi, which is 5 pi over 6. Or we could imagine the unit circle in our head and say, oh, I know exactly where that is. That's over there at 5 pi over 6. So what we're saying is that x equals 5 pi over 6, which means that cotangent of 5 pi over 6 is negative square root of 3. If you look that up, you should find that that really is the case. And example 8, use a calculator to solve for x in the given interval. Oh no, I don't even have a calculator here. Hang on, let me go get one. I wasn't expecting this. So the thing is that we can, if we have certain numbers that are trig functions of x are equaling, we don't necessarily need our calculator, but whenever, let me think, if it's not a special right triangle, then we will have to use our calculator. So if I look at this, cosecant of x equals negative 1.5. Cosecant, remember, is our hypotenuse over our opposite side, or we can think of it as r over y. We could go ahead and look at the picture of this, even though we are going to use our calculator in a sec. It specifies between pi and 3 pi over 2, which is down here in the third quadrant. And so this is negative 1.5 over 1. So really that negative is down here with the 1. We're going down 1. We've got a hypotenuse of 1.5. So actually that negative 1 is right there, 1.5. Now we could find that third side, but we don't need to. What's important to understand with using your calculator is, first off, they gave us an interval of radians, so we want to make sure our calculator is in radian mode. We're going to use the inverse trig function. If we're solving for x, we're using inverse cosine. We're doing inverse cosine. Sorry, we're going to do inverse cosine of the other side of our equation. And I personally, we can do inverse cosecant of negative 1.5. Let's do that on our calculator. So if you have an Inspire, there is an option for inverse cosecant. If you don't, then you're going to have to do 1 divided by, if you have an 84, and then you do secant, cosecant and sine go together. Okay? So it depends on what kind of calculator you have on how you would get this. Because cosecant is 1 over sine. And then we're doing inverse, so you have to press secant before you press sine. So let me do this real quick. So I get, whenever I do this, negative 0.729, and it repeats a whole bunch of times. And so 7297, because I don't really want to round up that 9. All right, so what that's actually telling us is this angle right here, okay? It's telling us that angle, the reference angle, and that's really important. It is not negative 0.7297 to get around to all the way to that line, or even to go this direction backwards, okay? Because think about it. This is going to be pi over 2 right here, negative pi over 2, so that's negative like 1.7, so we're not going far enough if we say that this is our answer. What we have to do, kind of like what we did up here, is we have to say on our calculator, it's going to tell us the reference angle, and then we have to then figure out, okay, what does that mean that my actual angle is? All right, so this angle right here that is what is 0.7297. I normally just ignore that negative personally. I just ignore the negative and move on. And so we need to do, this is pi, to get around there, we're doing pi plus 0.7297. So on your calculator, just figure out what that is. So you have to use the pi button plus 0.7297, which is 3.871. Okay, and that makes sense because it's between pi and 3 pi over 2, which is between 3.14 and 4 or 5 point something, which is what 3 pi over 2 would be. So that right there is going to be our answer.